Let us solve gate questions from torsion, which have appeared in mechanical engineering paper. The first question is, a solid shaft of diameter D and length L is fixed at both the ends. So there is a solid shaft which is like this. It has diameter of D and length is L. It is fixed at both the ends. Now, a torque T0 is applied at a distance L by 4 from the left end. So at the distance L by 4 here, there is a torque T0 applied. This is L by 4. So this is 3L by 4. Now the maximum shear stress in the shaft is, that is what we have to figure out. So how do we find out the maximum shear stress? So obviously we need to first see, this is like a parallel connection, because the two parts, this section here, this section and this section, both they twist and they have equal angle of twist. So because the angle of twist is same, so we can say that if the torque is divided into the ratio T1 Gj into L1, that is same as T2 L2 upon Jg. Now because both of them have the same diameter, this is only one shaft which has a diameter of D, so J will be equal and also the G is equal because it's only one material. So that means T1 into L1 is equal to T2 into L2, where T1 and T2 are respectively the reactions here. This is T1 and this is T2. These are the reactions. And obviously T1 plus T2 will be equal to T0. These are the two equations. So using these two equations, we can solve for the value of T1 and T2 respectively. So the value of T1, let's say we solve for T1. So T2 is T1 L1 upon L2. Substitute that in this equation. So we get T1 plus T1 L1 upon L2 equal to T0. So that means T1 L2 plus L1 is equal to T0 L2. That makes T1 is equal to T0 L2 upon L. That is the total length. Now L2 is nothing but 3L by 4. So this is 3 by 4 T0. Now if we substitute this value here, we get T2 is equal to 1 by 4 or T0 by 4. Obviously T1 is higher. So that portion of the shaft, which is the left portion, this portion, L by 4 section will have more shear stress because the torsion is higher there. So the tau 1, let's say, which is the left hand section shear stress, is equal to T1 upon J into D by 2, which is nothing but T1 is 3 by 4 of T0 divided by pi by 32 d to power 4 into d by 2. So this gives me, this is 32 into 3 T0 divided by 8 into pi d cube. So this cancels out, becomes 12 upon pi T0 by d cube. That is the answer. That is the maximum shear stress in the bar. Now the options which have been provided are, option A is 16 T0 upon pi d cube. Option B is 12 T0 upon pi d cube. Option C is 8t0 upon pi d cube, and option D is 4t0 upon pi d cube. So option B is the right option, 12t0 upon pi d cube. Now let's see question number 2. Yeah, question number 2 is a compressive spring is made of music wire of 2 mm diameter, having a shear strength and shear modulus of 800 MPa and 80 GPa respectively. Okay, the mean coil diameter is 20 mm, free length is 40 mm, and the number of active coils is 10. Okay, so there is a spring like this, where the mean coil diameter is this diameter. That diameter is given as 20 mm, while the wire diameter itself is 2 mm. This is 2 mm diameter of the wire. Now if the mean coil diameter is reduced to 10, okay, the stiffness of the spring is approximately. So in this case we have to see now the spring stiffness is proportional to the fourth power of the diameter of the wire by n into cube of the mean diameter of the spring. So in this case, let's say K1 is proportional to what is given as now the mean coil diameter is 2 to power 4 by number of coil is 10 into, and the wire diameter is 2 to power which is 2, so the small d represents the wire diameter, so it's 2 to, so this becomes 2 to power 4 divided by the number of coils is 10, and the mean coil diameter is 20 cube. So this is the original spring stiffness. Now when the diameter is changed, the mean coil diameter is reduced, but nothing else changes, so still the spring the wire diameter is 2, so it becomes 2 to power 4 multiplied by, or sorry, divided by 10, and the mean coil diameter is reduced to 10. So now K1 by K2 is nothing but basically 2 to power 4, 2 to power 4 is same, so it cancels out. 10 is also same, it cancels out, so it becomes 10 by 20 to power 3 or 1 upon 8. So that means that K2 is equal to 8 of K1. So what that does is, by decreasing the mean coil diameter, we are increasing the stiffness by 8 times. So let's see the answers. Options are decreased by 8 times, no. Decreased by 2 times, no. Increased by 2 times, no. Increased by 8 times. That's the right answer. So A is wrong, B is wrong, C is wrong, D is the right answer. That's the stiffness increases by 8 times. Now let us see question number 3. Question number 3 is, for a circular shaft of diameter d subjected to torque T, the maximum value of shear stress is, it's a very straightforward question. Question number 3 is a very straightforward question. Now for a circular shaft of diameter d subjected to torque T, the maximum of shear stress is, the shear stress is given by T upon J into D upon 2. That's the maximum shear stress, max. So if this is subjected to torque T and the diameter is T, so the value of J, polar moment of inertia, is pi by 32 multiplied by D to power 4. So this becomes 16T upon pi D cube. That's the answer. Let's see the options. Option A is 64T upon pi D cube. Option B is 32T upon pi D cube. Option C is 16T upon pi D cube. And option D is 8t upon pi d cube. Option C is the right option. Now let's go to question number 4. Question number 4 says two shafts AB and BC of equal length and diameters 2D and 2D are made of the same material. They are joined at B through a shaft coupling. Shaft coupling is such that it transfers the torque, or rather, let's say it's a very rigid kind of coupling, while the ends A and C are built in, or they are cantilevered. Okay, so this is the arrangement. This is the first shaft, and this is the second shaft. This is D and this is 2D, while this length is L and this length is also L, and this is a coupling here, right? So in this case, this is question 4. Now in this case, a twisting moment T is applied to the coupling, which means there is a twisting moment T here. So the twisting moment, when this twisting moment is applied, and TA and TC are the reaction moments here, or reaction torques here at the two ends. So this is end A, this is end C, and this is B. This is B. Now when this happens, the angle of twist is equal in both of them, which means that for this left shaft, I can isolate this shaft and say that there is a torque TA acting here, and this is twisting by theta. Similarly, this portion of the shaft, again there is TC occurring here, and this is also twisting by theta. So theta is, or the angle of twist is equal. So theta 1, let's say theta 1 is TA into L upon G into J1, or JA, let's say, which is same as theta 2, which is nothing but TC into L upon G into JC. JC is the second portion's polar moment of inertia. Now in this case, L and G are equal, so it cancels out. So TA upon JA is equal to TC upon JC. That's the relationship. Higher the diameter, higher its torque carrying capability. So now in this case, JA is pi by 32 t to power 4, and JC is pi by 32 into 2d to power 4. So if I put these numbers here, I get TC upon TA is equal to JC upon JA, which is nothing but pi by 32 is common, so that cancels out. 2d to power 4 upon d to power 4, which is nothing but 16, hence TC is 16 times TA. That's the answer. So now let's see the options. Options 1 is TA equal to TC. Option B is TC equal to 8 times TA. Option C is TC equal to 16 times TA. And option D is TA equal to 16 times TC. I'll just write the option D again. It is TA equal to 16 times TC. Now obviously again we can apply the elimination thing here. Both the shafts have equal length, they have same material, or they have different diameters, so obviously they cannot carry the same torque. This is wrong. So option A is outrightly eliminated. And because the lower diameter shaft will obviously be carrying lower torque, so TA cannot be more than TC. So option D is also not correct. So that leaves us with only two options: option number B and option number C. In both of them, TC is higher than TA, but the correct answer is option C, which is the TC is, or the right hand side torque is 16 times of the left hand torque. So let's go to question number 5. Question number 5 is a weighing machine consists of a 2 kilogram pan resting on spring. In this condition, with the pan resting on the spring, the length of the spring is 200 millimeter. Okay, so question number 5. In question 5, we have a spring and on which a pan is resting. It is like like this, and this pan has 2 kg mass. Now the spring is right now at 200 mm. So when the pan was not there, it must have been slightly higher because it is compressed now. So let's say that the original length is L0 of the spring. So that gives us a relationship saying that 2 multiplied by g, which is the acceleration due to gravity, is k into L0 minus 0.2. 200 millimeter is nothing but 0.2 meter. And assuming that k is the stiffness of the spring. Now that gives us one relationship, which is 2g equal to k into L0 minus 0.2, where k is the spring stiffness and L0 is the undeformed length or the original length. Now when a mass of 20 kg is placed on the pan, the length of the spring becomes 100 millimeter. So when 20 kg is placed, the total mass is 22. So 22 multiplied by g is k into L0 minus 0.1. So that's the second relationship. Now if you have to figure out what is the value of L0, we can divide these two numbers. So that gives us, if I do the division of this, let's say this is relationship 1 and this is relationship 2. So divide 2 by 1. That's what I'm doing. So if I do this, divide, I get 11 is equal to L0 minus 0.1 by L0 minus 0.2. So that gives me 11 L0 minus 2.2 is equal to L0 minus 0.1. So that means 10 L0 is equal to 2.1. So that means L0 is 0.21. That's the answer. That is the original length of the spring. Now let's see which option has L0 equal to 210 millimeter. That is the correct answer. So first option has option A has L0 as 220 millimeter. That is not the correct answer because the length L0 should be 210. The second option is B, L0 equal to 210 millimeter. That's the right option. Maybe let us see option C. Option C has L0 equal to 200 millimeters. That's also wrong. And option D has L0 equal to 200 millimeters. Again, that is wrong. So only option B has L0 equal to 220 millimeter for option A. Option B, L0 equal to 210 millimeter. Option C, L0 equal to 200 millimeter. And option D, L0 is 200 millimeter again. Obviously, there are some values of K also, which I have not written here because that is not required now, because we know what is the value of L0 and there is only one option with that value of L0, which is option B. So that's the right option. So you see, we don't need to solve for K in this case. We can simply solve for L0 first, and the original length, and that will be the guiding factor for us to figure out what is the correct answer. Obviously, if another option had L0 is 210, then we would have to solve the value of K. Now from this equation, any of these equations, we can put the value of L0. Let's say we put in first one. So L0 is equal to 0.21. Subtract minus 0.2 is 0.01. K, we can get K 2 into G upon 0.01. So that is around 2000 by, it's around, if G value is 9.81, so 2 multiplied by G is 19.6. So the value of K will be something like 1960, which is also there in option number P. Now let's see question number 6. Yeah, question 6. In question 6, a torque of 10 Newton meter is transmitted through a stepped shaft as shown in the figure. So there is a stepped shaft. It has 3 steps like this. and it is transferring a torque of 10 Newton meter. 10 Newton meter. So at this end also there is a reactive torque of 10 Newton meter because it is transferring that much torque. The torsional stiffnesses of individual sections of lengths MN, NO and OP are 20, 30 and 60 respectively. So this is M, this is N, this is O and this is P. So MN section has torsional stiffness of 20 Newton meter per radian. NO section has torsional stiffness of 30 Newton meter per radian, and OP section has stiffness of 60 Newton meter per radian. Now these are the torsional stiffnesses which are given for us. Now angular deflection between M and P, which is between this and this end, between M and P. What is angular deflection? So we have to see now, because this is a shaft which is in series, so each section takes equal torque. So if I isolate the sections, then I have first section, this is 10 and the reaction is also 10, this is 20. The stiffness, torsional stiffness, let us define that by capital K. So the theta is nothing but T upon capital K. So here theta 1 for this one is, let's say it is theta 1, and the torsional stiffness is K1, so that becomes 10 upon 20, which is 1 by 2. So theta 1 is 1 by 2. Similarly, we take the second one, which is 30. K2 is 30. That is the torsional stiffness for that. Again, it will be carrying the same torque, 10. So theta 2 is nothing but T upon K2, which is nothing but 10 upon 30, which is 1 by 3. Last one is the largest one that carries the same torque, 10. Again, its torsional stiffness is 60. So theta 3 is T upon K3. So that is equal to 10 upon 60, which is 1 upon 6. So the total deformation between M and P is nothing but theta 1 plus theta 2 plus theta 3, which is equal to 1 upon 2 plus 1 upon 3 plus 1 upon 6. If you do this calculation, we get 6. This becomes 3 plus 2 plus 1, which is nothing but 6 by 6 but 1. So that is the value of angular deflection between M and P. So the total twist is 1 radian. So let's see the options. Option A is 0.5 radian. Option B is 1 radian. Option C is 5 radian. And option D is 10 radian. So option B is the right one. Right. Now let's go to question number 7. Question number 7 is: a solid circular shaft of 60 mm diameter transmits a torque of 1600 Newton meter. The value of maximum shear stress developed is, that's a very straightforward question. What it says is there is a solid circular shaft of 60 mm diameter which is transmitting a torque of 1600 Newton meter. So we now know that the maximum shear stress is T upon J into D by 2, where T is given as 1600. J we have to find out. J is pi by 32 d to power 4 into d upon 2. So this becomes 16 into 1600 upon pi into d cube. Now d is 60 millimeters, so it becomes 0.06 cube. Now if we solve this expression, we will get the maximum, the shear stress as 37.72 into 10 to power 6 Pascal, which is nothing but 37.72 megapascal. And it's easy to see why we'll get this. Around 16 into 16 is 256, and pi is 3.14, and 6 cube is 36 into 216. 216 into 3 is around 6. So the first significant digit is 6 in the denominator, and the first significant digit is 24 or 25. First and second digits are 256. So 25 by 6 will be around 4. So 24 by 6 is 4. So it's around 37. The first one is 37. That's the correct one. So that's how you can solve without even solving. You can get the value of the stress. So the options are 37.72 MPa. That's the first option. Option B is 47.72 MPa. Option C is 57.72 MPa. And option D is 67.72 MPa. So this is the right option. Now let's see question number 8. Question number 8 is the maximum shear stress developed on the surface of a solid circular shaft under pure torsion is 240 MPa. If the shaft diameter is doubled, then the maximum shear stress developed corresponding to the same torque will be. Now the torque remains same. Now tau max, the maximum shear stress is T upon J into D by 2. Okay. Now in case of this, tau 1 is T remains same, and let's say the diameter is T, so this becomes 16T upon pi d cube. In second case, the maximum shear stress is 16T again because torque remains same, and the shaft diameter is doubled. So the shaft diameter is doubled means this becomes 8D cube because it becomes 2D. The diameter becomes 2D, so 2D cube becomes 8D cube. Now if we divide tau 1 by tau 2, we get 8. Which means that now that the maximum shear stress is, or rather tau 2 is tau 1 by 8, which is nothing but 240 by 8 or 30. So obviously it is easy to see why this is happening, that maximum shear stress is decreasing. Obviously it will decrease because we are increasing the diameter now. So when the moment we increase the diameter, D by 2 increases, but the polar moment of inertia decreases by 4th power. So overall there is a decrease in the shear stress. So the answer is 30. The options which have been provided are 120 MPa, option B is 60 MPa, option C is 30 MPa, and option D is 15 MPa. So option C is the right option. Let's see question number 9. Question number 9 says, two helical tensile springs of the same material and also having identical mean coil diameter and weight have wire diameters D and D by 2 respectively. The ratio of their stiffnesses is, obviously it's again a spring question. Question number 9. We know that the spring stiffness for helical spring rather is proportional to 4th power of the wire diameter divided by n into cube of mean diameter of the coil. This is the relationship. So now again we use this relationship. Now they have the same material, so obviously this relationship is again true, and they have the same mean coil diameter and weight. Okay, so now D remains same. So K1 is proportional to D1 to power 4 upon N N1 into T cube, because D is same. Let's say the same value of D, which is the mean coil diameter. K2 will be proportional to D2 to power 4 upon N2 into D cube. Now we have been given that D1 is D and D2 is D by 2. This is provided to us. The first coil has diameter D and the second coil has wire diameter D by 2. So that makes K1 is equal to, or rather proportional to D to power 4 upon N1 D cube, and K2 is proportional to d by 2 to power 4 upon n2 dq. These are the two relationships which we know. K1 by K2 is nothing but, now we can divide this relationship. We get d to power 4 upon n1 dq divided by d by 2 to power 4 upon n2 dq. So which is d cube cancels out. So this becomes d to power 4 by n1 divided by d to power 4 upon 16 n2. We can also cancel out d4, so that this k1 upon k2, that relationship becomes 16 n2 by n1, where n2 by n1 is the ratio of the number of coils. Now how do we find out the ratio of number of coils? There is another thing which is provided, which is that the two coils have the same weight. Now the number of coils is, for first case, let's say that weight of the first wire is number of coils in that multiplied by pi by 4 into d, which is its diameter square, into density of that. Now density is same for both of them, so we can just represent it by rho, while W2 is N2 into pi by 4 into D2 to power D2 square into rho. Now we know that W1 is equal to W2. It has been given to us. That means pi by 4 into, now D1 is D, rho is equal to pi by, this N1 is also multiplied here. So pi by 4 into N2 into D2 is D by 2. So this becomes D square by 4 into rho. So now from this we know pi by 4 gets cancelled out. This is D square and rho also get cancelled out. So we know that N1 is equal to N2 by 4. This is the relationship we know. So we substitute this in this equation. We know K1 by K2 is equal to 16 into N2 by N1 is 4. That is 64. That is the answer. So the options which have been provided are, option A is 1, option B is 4, option C is 64, and option D is 128. So option C is the right option. Now question number 10. A steel shaft A of diameter D and length L is subjected to torque T. Okay, so we have a steel shaft and it has been subjected to torque T. Its length is L and the diameter is D. So diameter is D and length is L. Another shaft B made of aluminum of the same diameter D and length 0.5 L is also subjected to the same torque. This is T. Now this is the other shaft. It is subjected to T. Its length is 0.5 L while the diameter is same as T. Now the shear modulus of steel is 2.5 times the shear modulus of aluminum. Okay. If this is G steel, this is G aluminum, so we know that G steel upon G aluminum is 2.5. This is provided to us. Now the shear stress in the steel shaft is 100 MPa. In this, tau steel is 100 MPa. It has been given. So how do we find out the tau aluminum? Now obviously we know we don't need to have the value of GS and GA here. Anyway, it is given to confuse us because that is not required. We know that tau max or tau steel is T upon J steel multiplied by L steel. So if I use this equation, I get the value of T that is T into L upon J is, this will become, sorry, this is not LS, this is T upon J into ds, which is the diameter of steel shaft, which is nothing but d. So it is T up. So this equation becomes tau s is 16 T upon pi d cube. That's the value of tau in that. Now aluminum also will have the same torque. So it's and it's because its diameter is d again, so the maximum shear stress in that will also be 16 T upon pi d cube. So essentially there is no change in the expression of the shear stress, hence both the shear stresses will be equal. You see, length and the value of G, ratio and D, all these are given to confuse us. Because the diameter is not changing and the torque is not changing, so the shear stress cannot change. The shear stress in both aluminum and steel shafts will be equal, and everything else has been given to confuse us. So please be careful of such questions. They can be solved very easily, but they are given to confuse us. So let's see the options which have been provided. Option A is 40, option B is 50, option C is 100, and option D is 250. So obviously option C is the right option. Both steel and aluminum shafts will have same shear stress, maximum shear stress, which is equal to 100. So these are all the questions which are there for the chapter on torsion, which have appeared in GATE Mechanical Engineering, and I hope you have got a clear understanding of what kind of questions come. Normally the questions are easy. Most of them will be either the step shafts or parallel shafts and spring questions, and because we are dealing with only circular shafts, so please remember the formula of maximum shear stress, which is 16 T upon pi d cube, and that will be the most important relationship actually.